Okay, I think we're ready to start discussing enzyme inhibition here, and I'm going to go over three main types of inhibition. So let's get started with the first one. All enzyme activity can be inhibited. Enzyme inhibitors can be classified according to three different mechanisms: irreversible inhibition, competitive inhibition, and non-competitive inhibition. Agents that bind covalently to enzymes and disrupt their function are irreversible inhibitors. So a few do bind non-covalently, and they are highly toxic. So I want to start with competitive inhibition because that's probably the most common one and the one you really want to get a good understanding of. Competitive inhibitors compete with substrate for the active site by binding reversibly with non-covalent bonds at the active site. So the key thing to know about competitive inhibition is whatever the inhibitor is that you're using is going to compete with the substrate for binding at the active site of the enzyme. So if it's competing for binding there, then what that essentially looks like is this. We have enzyme plus the substrate, right? Then this forms the enzyme substrate complex, okay? And then this goes over here to the enzyme, because remember the enzyme's like a catalyst. It's regenerated at the end in its original form. So enzyme plus product. So we have enzyme plus product. Now the place where the inhibition actually comes in is right here at the beginning. So what happens here is we have another way that this can go, and this is where we add the inhibitor. So if we add the inhibitor in here, then what's going to end up happening is, I actually shouldn't have put this here, I should have said plus. So enzyme substrate complex plus the inhibitor, now I can draw my arrows, gives me enzyme inhibitor complex. And that's your inhibition right there. That's exactly how this is working. This should be a plus sign up here, so it should be enzyme plus substrate plus some inhibitor, which is going to compete with the substrate. So all three of these are in solution at the same time, and it's going to form what's known as the enzyme inhibitor complex instead of enzyme substrate complex. So going back to the actual information here, competitive inhibitors compete with the substrate for the active site by binding reversibly with non-covalent bonds at the active site. So non-covalent bonds, hydrogen bonds, hydrophobic effect, etc. is ionic bonds are going to be what's going to be holding this inhibitor at the active site of the enzyme. They block the substrate from binding to the active site and forming the enzyme substrate complex. So that's exactly what I drew down here. Was that it's showing how this actually works, how this blocks that enzyme substrate complex. A competitive inhibitor will increase the Km. Now remember, the Km is the time it takes for this reaction to equal 1/2 Vmax. So to reach the point of 1/2 Vmax, or half the maximum rate of the reaction. Now, the competitive inhibitor increases the Km. Now that makes perfect sense because it's going to take more time and more substrate in order to reach the same Vmax. But the interesting thing about competitive inhibition here is that the Vmax does not change. So if I keep adding enough substrate, I'll wind up at the same maximum velocity. And that's exactly what I'm going to say here. The inhibition can be overcome by adding more substrate. The classic indication that something is a competitive inhibitor is that the Vmax is the same. So right there. So if I see these, and that's what we're going to do. We're going to look at the graphs here. I'm going to draw the graphs. I have a Lineweaver Burke plot down here, and I have a regular one over here. So first I'll show what it looks like on the regular velocity versus substrate graph here. And basically, if you recall, the original enzyme activity is usually just like this. It's like a hyperbolic type of curve here. And if we were to draw this whole thing out, we might say like right here, this is the Vmax. So Vmax right there, okay? And then after we have the Vmax, we'd have the point over here, which this is just a rough estimate. This is going to be my estimate for the Km. So this is the Km. So that's 1/2 Vmax. So 1/2 Vmax, okay? So that's our Km, and this is for, if I'm labeling this, I'm going to say this is for the normal. So this is for the normal, right? That's the normal enzyme activity. Now, if I add the inhibitor and it's competing, Well, remember, we're going to reach the same Vmax eventually, but what's going to happen is we're going to have a different Km, so the Km is going to increase. It's going to shift this graph over this way. So what's going to happen essentially, I mean, I don't know how accurate this is going to be, but essentially this is going to flatten out like something like that. So this is going to flatten out, and if I'm going to say this is, if I could write here, inhibited, or with the inhibitor. So if I look at the graph here and I see I got the normal enzyme substrate, the enzyme here operating normally, reaching Vmax and everything, and the 1/2 Vmax over here for the Km, but then I see that the graph is shifted over this way, so the new Km, so maybe I'll call that Km2, so the second Km for the inhibited version, or maybe I should have said KMI, it is shifted to the right, so we have a higher Km. Now, we can also draw the Lineweaver-Burke plot, which I'm going to see if I can get this on camera here. This is known as a Lineweaver-Burke plot. This is common. I discussed it a little bit in the video. It allows you to draw this as a line and express that same inhibition up there that I did up there as a line instead of a curve. So it makes it easier to understand and calculate the Vmax and the Km. So what ends up happening here is I have this here. I'm just going to draw a rough estimate, and I'm going to call this no inhibitor. So no inhibitor. So this is no inhibitor, right? So if I was going to then draw the new version with the inhibitor, I would draw something like this. So this would come right through here. And notice the slope is going to change, and that makes perfect sense. The slope is going to change because we're adding inhibitor and we're changing the Km. So maybe that's with inhibitor. Okay, so that changes. But the key points here, the key things to notice is that, look, right here, right in the middle, at that point right there, that's what's new. That's the intercept right there. Okay, that's the y-intercept, and the y-intercept corresponds to the Vmax. So this right here is 1 over Vmax. Okay, so that's 1 over Vmax, and notice they're at the same point. So you can see that that I'm not saying that the Vmax changed at all, because remember, with competitive inhibition, the Vmax doesn't change. That's our tip-off. If we see the same exact y-intercept for both the with inhibitor and without inhibitor, then we know that this is what's going on. We know we got competitive inhibition there. Now this point over here is negative 1 over Km. Now before you might be saying, well, why are you shifting? You're not increasing the Km. You know, yeah, I'm increasing the Km. It's becoming more positive over here. So this over here is your negative 1 over Km now. I'm trying to color code it a little bit so we can see it. So those would be the most important points on this graph. There's other things you can derive here and other things you may be asked to do. And I'm not going to go into those here. I just want to give the intuitive understanding of what's going on, of where you're going to be able to find the Km, where you're going to be able to find the Vmax, and to notice the difference here with this graph, the Lineweaver-Burke plot, as opposed to the normal curve here. Because you could be asked to draw these either way. Any of this is potential testing material. So let's go to the next page here, see if I can do another one before my time's up. This is already running long. Okay, so what I have here is what's called non-competitive inhibitors. They bind non-covalently to a site other than the active site. So they're not binding at the active site like the competitive inhibitor. They're binding at some other site other than the active site. And they change the conformation of the enzyme. So we saw this before. We saw this when we talked about like the induced fit model and things like that. Not that that's the same thing. I'm just explaining it in terms of the conformational change. There's a conformational change in the enzyme. This binds at a site other than the active site, and it induces a conformational change in the enzyme. So they do not prevent substrate from binding. Okay, so that's important. So the enzyme-substrate complex is capable of forming here. And unlike competitive inhibitors, they cannot be overcome by the addition of substrate. So I can't just add more substrate here. I just can't increase my substrate concentration and overcome the inhibition. That's not possible. And the non-competitive inhibitors will also lower the Vmax. So the original Vmax is going to be a little bit lower here than what it was previously. So, and the reason, and I should say here, that the inability for the reaction to proceed efficiently. So the reaction is prevented from proceeding efficiently, and that's why the Vmax is lowered. They do not lower the enzyme's affinity for substrate, because remember I said this can bind at a site other than the active site. So the enzyme is free to bind the substrate, no problem. It just can't do anything. It just can't do anything after that. So it can bind the substrate. It's just not going to, the reaction is just not going to be as efficient. So the Km, so what that means is the Km remains the same. Now for this one I only have the Lineweaver Burke plot here. So what I want to do with that is I just want to draw my uninhibited version, or my normal. So I'll just draw a line through here if I can get my marker to work here. Okay. So right here. So this is no inhibitor. Okay. So we got no inhibitor right there. Now remember what I said before, that the Km is not going to change. That means we're going to have the same Km over here. But the Vmax is actually going to decrease. So if I'm going to draw that line, I'm going to start from the same point. I'm going to do something like that. And I'm going to say that is with inhibitor. With inhibitor. Okay? So the points, again, to notice here is, look, we have different. Look, this is 1 over Vmax. And this part over here is 1 over Vmax. Okay? This is the Vmax. So notice the Vmax is actually becomes lower here. We're shifting the graph up. The Vmax is actually decreasing because remember this is the inverse. It's 1 over V that we're plotting here. And this point over here is negative 1 over Km. And so that's the way we find our Km. But notice it's the same point. They're coming from the same place. Okay? So that's the key for non-competitive inhibition. It binds to a site other than the active site, and what's going to wind up happening here is you're going to change the Vmax by decreasing the Vmax, but you're going to increase, or you're going to rather not increase, you're going to keep the same exact position for the Km. So you're going to have the same Km. It's not going to affect the enzyme substrate binding. Now, the last one I have here is on competitive inhibition. The inhibitor binds only to the enzyme substrate complex. Okay, this binds only to the enzyme substrate complex. This is what's known as on competitive inhibition. So let me see if I could show you what that looks like here. So what that ends up being is, look, again, enzyme plus substrate. That's our normal thing, right? We add some enzyme, we have some substrate. This forms what's known as an enzyme substrate complex, correct? Okay, we have the enzyme substrate complex. Now, with that, I'm going to add the inhibitor just like we did before, but notice it's now going to, it's not over here like it was with competitive inhibition. It's over here with the actual enzyme substrate complex. And that is going to come down here and form enzyme substrate and the inhibitor. Okay? So that's the difference. That's one of the big differences here. So to finish this up, let me just go back through this one more time. The inhibitor binds only to the enzyme substrate complex. This type of inhibition decreases the Vmax due to less availability of the active complex. The Km will decrease due to better binding efficiency. So there'll be better binding efficiency, but there'll be better binding efficiency, but the Vmax will decrease. Okay? So if I was drawing that, I'm just going to again draw a generic line here and say that that's no inhibitor. Okay, no inhibitor, and then I'm going to show that my Vmax is increasing here. So again, this is negative 1 over Km. This is also negative 1 over Km, but this is for the inhibited version. Okay, and notice that we have a difference in the 1 over Vmax in both places here. Okay. So let me get that on screen so you can actually see what the hell I'm doing. And now you got it. So hopefully this is helpful. I know this ran a bit long.